So today we'll begin Chapter 6. Let me start by asking a question. If, when you were born, your parents had invested $10,000 into your bank account, do you think you'd have enough money to go off to college when you turn 18? This chapter will help us decide that. First, let's open up your journal to page 156 and fill in the 6 vocabulary words. Next, let's look at the first core concept. This is the graph of, is the parent function of an exponential growth model. Notice the graph shoots off up into infinity. It grows quickly. It grows exponentially. We also can write an equation for the exponential growth model. And what that would look like is y equals a times the quantity 1 plus r to the t power, t standing for time. Now let's look at the next core concept. This is the parent function for exponential decay. Decay is when the base number b is between 0 and 1, whereas the growth b was greater than 1 for growth. Decay, the b is between 0 and 1. We can also have the exponential decay model, which is similar to the one we just wrote on our last journal page, except this time into y equals a times the quantity 1 minus r raised to the t power. So minus for decay, and it was plus for the growth. Now let's look at examples 1, 2, and 3. So let's move to our notes packet. The first thing we want to do is look at the two equations and decide if they're representing exponential growth or decay, and then we'll graph. So to decide growth or decay, you want to look at the base number, and in A, the base is 2. And 2 is greater than 1, so this is going to represent a growth. Next thing you want to do is graph this equation into your calculator, and we can pull up a table. So you can see here in my calculator, I graphed the function 2 to the x power, and then I pulled up my table. And let's try and stick with just plotting the points -1, 0, and 1. So let's transfer that to our notes. So I transferred the points to my table, and now let's plot them. -1, we have a point at a half. At 0, we have a point at 1. And at 1, we have a point at 2. Next, I'm going to connect my dots in a nice smooth curve, and notice it's going to shoot up exponentially, like a growth. Now let's try B. Notice the base number here is 1/2. 1/2 is between 0 and 1. Therefore, this represents a decay. You're going to do the same thing by entering this equation into your calculator and pulling up the points from -1 to 1. This time the points will be 2, 1, and a half. So let's graph that onto our notes. At -1 we have a point at 2, 0, 1, and at 1 and a half. Connect in a smooth curve, and notice this time we have a decay. The graph is shooting downward. We'll then look at the monitoring progress in class. Prepare any questions you might have. Let's move to example 2. We're going to need those models that we had written in our journal. We have y equals a quantity 1 plus r to the t for growth, and we have it with 1 minus r for the decay. So you might want to pause the video and read example 2 to begin. You can see the equation here is similar to one of the equations above. In fact, the 0.85 is smaller than 1, which means that we are looking at an exponential decay. So we have 0.85. We have 0.85 as our r, so we can actually figure out the annual percent decrease, since we're talking about decrease, since we know 0.85 is the r. So if we use our generic formula at the top of the page, we could do 1 minus 0.85 and get 0.15, which is equivalent to 15%. So the car's value will decrease 15% per year. To estimate the value of the car when it's 8,000, which year that will happen, you're going to need to graph this. So let's graph the equation into our graphing calculator, and then we're going to trace our graph until we see when y is 8, because the graph will be in thousands of dollars. So look for when y is 8 and then tell me whatever x value you see on your calculator screen. So let's try that now. After graphing the equation, you can see I can only barely see part of my graph. So I'm going to change my zoom, change your window, and I can zoom out a little bit. Alright, so that's much better looking. Now we're going to trace. So press menu, trace, and then do a graph trace. And you can see at the bottom I have my x and my y coordinate. I'm looking for when y is 8. So I'm going to continue tracing until I get as close to 8 as I can. It looks like, so as you can see, as close as I can get to 8, I'm at about 6.9 or 7. So let's write that into our notes. X will equal about 7 years. The car will be worth $8,000. Monitoring progress we'll look at in school. Now for example 3, we're going to do the opposite. We're going to try and write the equation. Let's see, we are writing a growth model, so the generic growth model that we had written at the top of the page, right here. Let's recopy that in front of example 3. So we have the generic equation, y equals a parentheses 1 plus r to the t. A is like your starting value, and in this case, the starting population is 6.09. Then 1.18% is our increase, so this will be our R value. So let's try plugging in. We have y equals, our A is 6.09, then we have 1 plus, R is 1.18%. Change that to a decimal, which will be 0.0118, all to the t power. You can add 1 and 0.0118 and get a final equation of 6.09 times 1.0118 raised to the t. And then we can do whatever we need to do with this equation. They want us to estimate the year when the population is 7 billion. So again, ask yourself, what's the 7 representing? The time or the y? So you're going to want to graph the equation that we just wrote and look for when y is 7 billion. You're going to graph it and then trace it. And after tracing it, the closest x value when y is 7 billion should be about 12, or it should be t equals 12. So the time will be 12. We'll then do monitoring progress number 6 in class. Please have any questions you have ready for class tomorrow.